In exercise 2c, we will talk about the steps that are necessary for fitting a tree. So how does this procedure of fitting a tree is different from a linear regression, or from the fitting of a linear regression? To fit a regression tree, we will start with a loss function. And this is pretty similar to the OLS estimation, because if you think back in the OLS estimation, our loss function was the sum of the squared residuals. And here for the tree, our loss function looks pretty similar, because it's also, here is an error, so the difference between a prediction and a true value. This is squared, and then it's summed up over all the predictions we consider. So pretty similar to the sum of squared residuals. The difference is we minimize this in respect to the regions R1 to Rp and the estimated values within these regions, which are y hat R1 to y hat Rp. Now, once we have the regions, those y hat are easy to calculate, because they are simply the average values, the average y values of the points in our regions. But since we minimize the loss function in respect to these regions, we cannot use the first order conditions, because you cannot differentiate the loss functions in respect to those regions. So we have to use another approach. We will use recursive binary splitting, which means we take our feature space and we split it up into subregions. We will use a top-down approach, which means we begin at the top of the tree and then split sequentially until we end up at a point that we consider optimal. And we will use a greedy algorithm, or this is a greedy algorithm, because it only considers the split that we do at the point of splitting and no further split in the future. So at the current step, we split and we will evaluate the split, and we won't evaluate it in respect to future splits, just the split we do right now. And this neglection of any future splitting is called greedy. So this way, the feature space will be split up in partitions, and how do we decide where to split? Because when we have a partition with multiple observations in it, we could basically split after every observation or between all the points. And we will evaluate the loss of each split by calculating the MSEs. So after every point, we will split and then see the partitions that result from the split, then calculate the loss, save that, then we split again and at another point, and again and again and again, until we have all possible splitting scenarios, and then compare these splits, and the one with the smallest loss will be the split that we actually take, because this is the most optimal one. It produces the smallest loss. And as we said, since it's greedy, we won't have a look at which split that might be resulting from this partitioning later could could produce a small loss, we just say, okay, now splitting this partition at hand, what is the smallest loss possible, and then we can take this partitioning. So we could just continue splitting, basically, until everything is split and there's a region for every single point. However, then this would be total overfitting, because then there's a region for every point, and that's basically just saying, okay, we have now the data set itself. So we want to implement a stopping criterion that says up until a certain point we will split, but once this criterion is reached, we will stop. And we will then end up with the model where we stopped. So for example, we could say our tree should have a certain depth, and then we, for example, it should only have 4 terminal nodes or 8 terminal nodes or whatever, and then it will only split until this number of terminal nodes is reached or until a certain depth is reached. But there are also other stopping criteria. Exactly. So we implement the stopping criterions so we won't end up with a region for every observation.